Assalamualaikum and hi everyone. Today our group will present about topic per unit system in electrical power system analysis. So to get started, I will introduce ourselves. My name is Adelatas bin Abdul Rahman and my fellow member is Syed Muhammad Zaki bin Syed Zakaria and Tisan anak lelaki Mandi Rajan. The topic that given to us is per unit modeling and analysis of a multi-voltage three-phase power network. First of all, the PBL scenario is a power utility supplies an industrial facility through a three-phase transmission system. The system consists of a synchronous generator, two transformer, one transmission line, and an industrial load. The network arrangement is shown below. Generator G1, two transformer T1, two transmission line, two transformer T2, then industrial load. The engineering team must develop a per unit model of the system to support future load flow and short circuit analysis. So our group has been appointed as the junior power system engineering team to prepare the technical report and present the finding. Single line diagram and voltage zone identification. So based on our scenario, there are three zones. The first zone is when the generator produces 13.8 kilovolt before the voltage is stepped up by transformer T1. So as you can see on the single line diagram, the generator G1 will will supply 13.8 kilovolt to transformer T1. Then at the zone 2, transformer T1 will increase the voltage to 132 for efficient power transmission through the transmission line. Then on then from the transmission line, the from transmission line 132 kilovolt, the transformer T2 reduce the voltage from 132 to 33 kilovolt to industrial load. So it will supply the industrial load safely and efficiently.
Hello everyone, well, my name is Station Sanam Manirajan and now I'm going to present the calculation phase for our project. So let's begin. We divide our power system into three isolated voltage zones based on the transformer location. For zone 1 on the generator side, we select its rated voltage of 13.8 kV and then multiplying by the turns ratio of transformer 1 gives us a high voltage transmission zone 2 base of 132 kV and stepping down through transformer 2 onto the load distribution side yields a zone 3 base of 33 kV. Utilizing this baseline voltage alongside our common system power base of 100 MVA, we apply standard 3 phase electrical formulas, which is I base is equals to S base over Z 3 times with V base to solve the task for which giving us our baseline currents. First is 4.1837 k ampere for zone 1 and also the second one 0.4374 k ampere for zone 2 and also the last one which is 1.7495 for zone 3. Moving on to the next part, which is task 5, establish our base impedance using the formula of Z base is equals to V square base over S base. This yields a baseline impedance of 1.9044 ohm for zone 1, a much higher 174.24 ohm for the zone 2 transmission line, and also the last one which is 10.89 ohm for zone 3. With these baseline values ready, we convert our physical grid components onto our unified system base by using the formula which is x new is equals to x old times with s base new over s base old times with v base old over v base new square. For task 6, we shift our generator G1 from its original nameplate reactance of J0.20 pu on a 50 MVA rating up to our common 100 MVA base doubles its value to J0.40 pu. For task 7, convert transformer which is T1 from its 60 MVA hardware base results in J0.1667 pu. Lastly, for task 7, we normalize the transmission line by dividing its actual physical reactance of J40 ohm by our zone 2 base impedance, which gives us J0.2296 pu. Now that all individual components parameters have been converted to task 12, which compiles them into a single unified circuit layout known as the equivalent per unit reactance diagram. By normalizing the network, all physical transformer boundaries and turns ratio are completely eliminated, leaving us with a continuous simplified single phase network running from the generator source down to a common neutral reference bus. Moving left to right along this single series loop, we start with our ideal internal generator voltage source, which is EG1 operating at 1 pu, followed by our calculated reactance, the generator at J0.40 pu, transformer 1 at J0.1667 pu, the transmission line at J0.2296 pu, and transformer 2 at J0.20 pu. The entire circuit loop terminates at our industrial plant load impedance of 2.8337 plus J1.7558 pu, giving us a total network grid impedance of J 0.9963 pu before the load, which served the ideal baseline tool for future circuit faults, studies and system modeling. That's all from me. Thank you. Bye. To conclude the component conversion, task 9 shifts transformer 2 from its original 40 MVA equipment base up to our 100 MVA system base, providing a final per unit reactance of J0.20 pu. Next, for task 11, we determine the equivalent per unit impedance of our industrial plant unit, which draws 30 MVA at a 0.85 lagging power factor. Since it operates right at its rated voltage, which is 33 kV, it operates voltage is perfectly 1 pu. We first resolve the apparent power into real and reactive components, which gives us a complex per unit power load, which is S load pu of 0.255 plus J 0.1580 pu under our system base. Finally, applying the network relationship, which is Z load is equals to V square load over S conjugate, using the complex conjugate of our power yields our final equivalent load impedance of 2.8337 plus J 1.7558 pu. This concludes all individual components parameter calculations.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhammad Zaki bin Syed Zakaria. Nama metrik saya B1124107175. So, saya akan menerangkan slide presentation saya, iaitu advantage of per unit system. The per unit PU system provide many advantage in electrical power system analysis, especially for the network operation and multi-voltage level. Firstly, it simplified calculating the multi-voltage power network by expressing all electrical quantity on the common base. This element that need to repeatedly convert the quality between different voltage level, making calculate faster and less prone to error. So secondary, the per unit system convert a largest physical quantity such as a voltage, amperes, ohms, and MVA into the smaller dimensionality value. That a value are easy to interpret and compare because that compressed relative to a selected base value rated they are actually magnets. Next slide is another advantage is the allow the parameter of the generator, transmission and transmission line, and a loaded become a compare directly on the same base. Since all components are represented in per unit value, engineer can easily evaluate the relative electrical characteristic and contributed to the overall system performance. The unit also simplify transformer modeling. When using actual unit, transformer turn ratio must be considered repeatedly during calculation. In the per unit system, the transformer independent remain essentially unchanged across the transformer, reducing the complex of a power system analysis. Next is furthermore, the per unit system improves correctly when the analysis voltage division, impedance level, and overall system behavior engineer can quickly determine whether a quantity is above or below its value by observing its per unit magnitude. Finally, the per unit system is widely used the low load flow studies, false analysis, transient stability studies, and digital power system simulation. Its ability to represent different equipment on the common base make it a science tool for the model power system planning, operation, and analysis. Next, my slide is engineering interpretation. The calculation per unit value indicate the relative electrical behavior of the each component with respect to the selected system base. The largest per unit reactance indicator the stronger opposition to the current flow and contribute to the larger voltage drop during operation. The generator reacted present the internal independence of the machine, while the transformer reactance present voltage regulation and full current limiting a characteristic. The transmission line reacted show the impact of the line on the power transformer capability. The industry power, the industry load per unit independence represent the electrical demand placed on the net. And then that value are usually for the determine system performance during a normal operation and fuel condition. And then slide yang terakhir daripada saya iaitu conclusion. This project successfully developed a complete per unit model of a three-phase multi-voltage power network. Their voltage zone based a quantity equipment reacted, transmission line independent, and a industry load a parameter where a converter into a common 100 MVA per unit base. Their result demonstrated how the per unit system simplifying power system calculation and provide a common platform for analysis component operating at a different voltage that a developer per unit model can be used the foundation for the future load follows studies and short circuit analysis and power system simulation. Thank you from me.